From my understanding, V3 loop, you have to use that for systems if you're concerned about the charge kind of, I don't know what the right word is, like diffusing away further than it should. So I guess like if you're dealing with metal clusters, it's like if you're dealing with very localized charges, it's probably not as ideal.
Yes. No, the example you are referring to is maybe something you need to use a hybrid function. Obviously, you can always like validate. So if it's like a single calculation, like a single point calculation or something.
Right, just be your energy barriers.
See, yes. In our case, we have to do many DFT calculations. So we could take some static systems and do a validation of different functionals, compare them, and also try to see if there's experimental properties, observables we could compare with. So that's what we always do. To take some simple setup for which there is an experimental number and see how bad we are, or how good typically or not, never spot on.
Same order of magnitude though, if you can get there.
Yes, I mean if you're 10 kcal off for like relative energy, so for static calculation, productive reactants, it's quite a bit, 10 kcal, but if it's 3 kcal, then it's fine.
Is it okay if Aaron starts first? Okay.
So yeah, I didn't put my name on the slide, but I'm Aaron. And I guess you're probably familiar with some of our research that we do with Dimitri. It's mostly excited state dynamics. So we use molecular dynamics basically just as a tool, so we can extend that to our excited state dynamics. And I didn't go into much as the excited state models that we have. So basically, I was just going to show just interesting examples of molecular dynamics we use and some interesting chemistry that we can see in these systems. And so I guess the systems I mostly focus on is quantum dots. And so if you've been familiar with the energy literature at all the past 10 years, you've probably heard the word perovskites thrown around a little bit, and this is what this is attempting to model. So it's a perovskite quantum dot. So the inorganic interior, that's the lead halides with some counter ions, which just kind of are sitting there to keep the crystal structure stable. And then for a quantum dot, they're in solution, so you have to put ligands on them to make them soluble, and to passivate the surfaces so that they're bright emitters, because that's usually what you want from a quantum dot. And so that's what this model is here. So it's passivated with ligands that are shown in experiment, except they're just shorter chain.
Yes.
So it's the same functional groups though. So you have a deprotonated acid group here, which binds to all the surface leads, and then the proton that's deprotonated gives it to an amine, which makes it an ammonium, and then that coordinates the surface of bromine. So in this case, it's mostly coulomically stabilized. And experimentally, they find that it's not the best surface passivation technique, because the ammoniums and the acids are basically like aligned right next to each other, and so it kind of makes it liable for that proton to transfer back and forth between them, and so it makes some of the ligands desorbed and hurts the samples. And so I was just going to show some molecular dynamics videos and some observables that we've seen from that system. And then another model that we've been looking into is doping quantum dots with transition metals. And so this is the same model as shown here, except the transition, we dope it with a manganese 2+ ion directly in the middle of the quantum dot. And that's shown here. So it's manganese 2+ and mostly octahedral field. And what we were trying to model was our experiment they found that if they doped them, these quantum dots with the transition metals, they were getting DD or signatures of DD transitions. So like a broad emission peak around 600 nanometers. And usually that's attributed to DD optical transitions. And then we were trying to model that as well. And then I was going to show some interesting features that we saw from that model. And so just from the surface chemistry, I'll show electrodynamics video just so you have an idea of what you're looking at.
Yes.
Like all these carboxylic acids on the surface, they're bonded to the lead, and they have a certain distance, and then the ammoniums kind of are just spacers in between, and they coordinate with the bromians. And if I go to the video, it's chromy resolution, but you can see a lot of vibrant chemistry going on here, so you can kind of see that the acids that kind of coordinate with the hydrogens, and you can see that there's, where's a good one to look at? So this guy up here, you can kind of see that he's orbiting from the surface, and he's mostly just interacting with the amines instead of staying stuck onto the surface.
What is the temperature here?
So this was done at 300K for our model, so it's just molecular dynamics done at 300K. And there's all sorts of vibrations at the surface which pump into the crystal as well. So it's mostly the acids that are bonding to the lead surfaces. And then they introduce like bending modes and possibly even some stretching modes,
Yes.
which can act as like a heat reservoir for if you have an excited electronic state, that the electron donates its energy to those vibrations. And so
This is what you expect or what you have been seeing in your...
So we actually did excited state modeling on that. I didn't put in any results because I was just told to throw something together pretty quickly. But that turned into a JAX paper. So it was, and we got some observables that were same order of magnitude as the CEAN experiment in terms of like hot carrier cooling times and then photoluminescence quantum yields. So. And then, this is just showing the bond distances on the surface for if it was at just 0K. And then what I did is for each time step, just did an RDF. And you can see that the bond distances fluctuate time. And so these are just between the leads and then carboxylic acids. So this peak here would be the lead oxygen. You can see that fluctuates over the molecular dynamics trajectory. And this one's just the oxygen.
These are all distances, yes.
Yes. Then each peak just corresponds to a different distance.
Yes.
And then if you're looking for just a single event, it's not very helpful. Like if you're looking for a specific transfer of a bond or breakage of a bond. But it's interesting to look at just if you're looking for something interesting in your model.
Yes.
And then you can go backtrack and then look at the time
So
steps.
you have like one picture, if something happens somewhere, then it comes up apparent in this movie.
Mm-hmm. And then for the manganese ones, there's an interesting feature, which I'll go to later. And then this figure I put below is just showing as you have bond fluctuations during the trajectory, it impacts the optical properties. And so this is just a plot of time during the trajectory versus oscillator strength, which oscillator strength is just basically how likely the model is to emit light, or nanocrystal. So basically the high peaks means it's very bright, it's a high probability of emitting a photon, and then if it goes to 0, it turns dark. So this is just showing that during the trajectory that has changing bright and dark features.
So it's same as blinking, but 6 orders of magnitude quicker.
Yes, because I guess I'm blinking. It's an ensemble effect, so they measure those on seconds. But and this just kind of shows that the dynamic bonding at the surface is not ideal if you want a stable emitter. Because if you want, I don't know, something like if you were into like quantum information. It's like you want your emission to be pretty stable throughout the entire time and not change. So yeah, those are some interesting observables for the surface chemistry of that model anyway, and how it impacts the optical properties. And then this slide is just for the manganese doped model. So we'll look at the YouTube video that Dimitri put up. And so same model, and then the orange is the manganese in the middle. You can see it's coordinated with bromines on the extended sides. And the video isn't as vibrant as the other one. But during the trajectory, I guess.
It doesn't show the initial stage of trajectory.
Right. That's just like a snapshot.
It's maybe last stage.
Yeah. But an interesting part of that is during that part of the trajectory, it transformed. That's not what I wanted. It transformed from initially at 0K just optimized. It was in an octahedral field, but during the trajectory, it seemed that it kicked off two of the halides and went to more of a tetrahedral. And so that's kind of interesting because
it's like a captive with tight arms, breaks
Yes.
rope and releases into.
And so these were bromides that were the halides that were, they went where?
so they coordinate with the lead. So if I go back to the video, you can kind of see them. So you can see one. So the halide we'd expect to come out of the plane here. It's like it's
Yes.
stuck to the left there, and then the other one. I think it's hard to see, but I think it's on this side. So basically, they just bonded to the surfaces, and that's kind of interesting because I guess the spin states of these of dopants is very sensitive to the coordination geometry. So it's probably even going to change oxidation states too if it goes from octahedral to tetrahedral. And so implications for that is like optical stability for its emission, and then also for magnetic properties too. If we don't specifically focus on those, but it's going to change because normally it's in a low or a high spin configuration, and it could just change something completely else. And a possible avenue of research would be like, if you heat these up to different temperatures, could you turn it into some sort of switch
Yes.
between spin states? And yeah, the last thing I'll show is just the RDF video that shows the bond distances between the manganese and the bromine, and that kind of shows that there is definitely a change in coordination along the trajectory. So there it's not doing much. And you kind of see about here it broadens and then
Yes. So you see the
peaks.
shoulder and then.
Oh. So it probably donated one to the outside lattice and eventually took it back.
Yes. Yes. So this was the same time periods, the movie and RDF.
They're different time periods because, well, I guess I did the RDF. Dimitri made the video, so I guess I'm not exactly sure which snippet of it he used.
Yes.
But I mean, it's always possible to go back and splice the whole thing together.
Sure. Yeah.
But I would assume since there's like two drastic changes that the snippet that Dimitri got was there's a contraction and elongation.
And what kind of theory you have been using for this?
Oh yeah, so this is all DFT, and we're using PBE,
PBE.
functional for all the molecular dynamics. And then all the trajectories are roughly 1 picosecond. And then it's that 1 femtosecond time steps. So.
Yes.
And yeah, that was the last slide I had. So.
Thank
Yes.
Questions, or it was enough discussion? So there will be one more. Dr. Liu can show something about his.
Say your name.
Aaron? Aaron, AAR1.
So I'm going to talk about some examples by using molecular dynamics to understand chemical reactions. So specifically, I'll focus on 2 examples. The first one is photopolymerization of CHS. The second one is thermal grafting of benzonium salts on silicon surface. Okay, so what is CHS? So this is a chemical formula for CHS. So it is a colorless liquid at ambient conditions. So actually, this kind of compounds has attracted much attention because it can be used as silicon sources to prepare silicon-containing materials using liquid-based fabrication techniques. For example, you can use them to fabricate silicon quantum dots, silicon nanowires, thin films as well. And actually, it is also a good alternative to monosling in chemical vapor deposition technique. So this is a picture of CHS. As we can see, it is colorless liquid. And actually, there is a chemistry for this kind of compounds. So starting with CHS monomer, if you shine the light or heat it up, it will transform into polymer through some ring opening polymerization reaction. If we heat it up further, we can transform the polymer into amorphous silicon. And under additional treatment, you can change the amorphous silicon to crystalline silicon. So this kind of reaction pathway has been suggested by experimentalists, but the computational work is missing. So that's the reason we are focusing on this reaction. And we published this paper in GPCO last year.
Is there also other ways of converting monomers to dimers to amorphous silicon? Not by photo-induced reactions, but by other.
So far, it is either by photon or either by heating.
Yes. Yeah.
So we are interested in photochemistry. So the method we use is so-called time-dependent excited state molecular dynamics. So, and the detail can be found in this paper. Actually, the TDSMD refers to molecular dynamics with time-dependent electronic configurations. So here is a picture describes the process. So the blue one is the ground state potential energy surface, and the red one is the excited state potential energy surface. So the ground state PS is a little bit weird because you have this bump, but we use this bump to indicate there is a reaction barrier. You need to overcome this reaction barrier. So in our calculations, the electrons are hawking between ground state and excited state. So first the electrons are promoted from ground state to excited state, and then it relaxes back from excited to ground state. This is called a Rabi cycle. In our simulations, we have many Rabi cycles. And during this Rabi cycles, the system accumulates kinetic energy so that it will finally overcome the reaction barrier. So this is one example. So for CHS, we want to model the photopolymerization, but for polymerization, you need hundreds or thousands of monomers. It's not possible. So instead, we just focus on 2 monomers. And this is for a face-to-face configuration. This is one CHS, this is another CHS molecule. So this is just one trajectory. So actually, for the first part of the trajectory, because the accumulated kinetic energy is very small, there is not much reaction happening. We can only see the breaking of the silicon hydride and reforming of this bond. But as time goes by, there is more energy in the system, so we can see much more reactions. At this stage, we can see other hydrogen atoms are also active, and we can see abundant silicon hydrogen breaking events. So there might be some hydrogen transfer reaction going on as well. So at this stage, you see the ring structure is not stable. You can see the breaking of the silicon bond here. And finally, we can see dimerization reaction here.
So by now you have added a substantial amount of energy.
Right.
Yeah.
That's the reason we can see the fragmentation of this kind of complex. So now we have the trajectory, and we want to analyze intermediates in the trajectory. But I guess there is one point I should mention. So far the system has so much kinetic energy, so we need to remove the kinetic energy. What we did is we extract intermediates from the trajectory, and then we run geometry optimization calculations. So here is some example. So this is our starting point in the TDSM calculations. This is one intermediate. So this is geometry optimized intermediates. So we can see the dimer, right? And here we see the dehydrogenation of the dimer. And at this column, I calculated the density of states of intermediates. So what we found is, as time goes by, we can see the shrinking of the band gap. So at here, this is occupied states. This is unoccupied states. So this is the band gap. And here, it's most half. So here I show the experimental absorption spectra. So, as a function of UV irradiation time. So 0 minutes, there is no UV, and we can find the band gap for the monomer is like 5 electronvolts. And at this time, at 80 minutes, we can see the band gap is about 4.4 electronvolts. So, and at this stage, this corresponding to early stages of photopolymerization. So our results is in qualitative agreements with computation. This is another set of data we can get from TDSM trajectory. This is energy profile. So we can see the activation energy for this kind of dimerization reaction is about 2.7 electronvolts. We can also get the mass spectrum from TDSM trajectory. And this is different spectrum corresponding to different starting point for TDSM calculations, as well as for different excitation conditions. So basically, the most intense peak is the monomer. This is because most of the reactions happen in the second half of the trajectory. But features in this band corresponding to fragmentation, and features in this band corresponding to the dimerization. I guess so. If we have experimental data, we can compare the computational results with experimental one.
And so experimental data is
It's not
difficult to generate, or
right for this kind of compound. It's very air sensitive, so my
you need
spectrum is a little bit different.
so So it's difficult to do this in a controlled, proper environment.
Right. So this is another example. So here we focus on thermal grafting of diazonium salts on silicon surface. So typically silicon surface is passivated by hydrogen, but there is one problem, which is thermal stability. If we increase temperature, the silicon hydrogen bond will break, so which is bad because if it breaks, that means oxidation reaction might happen, which is very bad for photovoltaic applications. So one method to overcome this problem is to introduce a protective layer at the surface, at the silicon surface. And one agent to do that is diazonium salt. By using diazonium salt, we can form a silicon carbon bond on the surface. And this paper shows the mechanism of this reaction. So here is a silicon passivated. This is a hydrogen passivated silicon surface, and this is a diazonium salt. This is anion. This is cation. So under some conditions, there will be electron transfer from the surface to the cation. Because of this electron transfer, we have radical on the surface, and this cation will turn into a radical. Since it is a radical, the carbon-nitrogen bond is easy to break, so we can eliminate this nitrogen-2 gas. And after doing that, we have radical here, and this is the anion. The anion can attack the proton, so we can eliminate this HDF4. And now we have radical at the film group, we have radical at the silicon surface. They can easily recombine, so the film group can be kept on the silicon surface. So we want to model this reaction. This is our simulation cell. This is the silicon 111 slab. And this is the diazonium bromide molecule. So what we did is we sampled different initial geometry from room temperature molecular dynamics. So this is one example. This is a snapshot at 800 femtosecond. So, and also to reduce computational cost, we fix all other silicon atoms except the very top one, because we believe these silicon atoms will not contribute to the chemical reaction.
And to what extent do you save computational cost if you fix the atoms?
I guess maybe I'm not sure how to quantify, but
Because this is the whole box is a DFT box,
yes,
so you still have to do the DFT each time step in your dynamics MD.
right.
It will be interesting to assess degree, but opening each ion for molecular dynamics wouldn't quicken the DFT part, but it will create additional uncertainty and say bifurcation points, and so it will be longer and more.
Yes. So you reduce your configuration space and focus on
Right.
the
Right.
Fair.
And there is another trick we use to model the chemical reaction. So actually, to model chemical reaction, we use high temperatures. The temperature is 2000 Kelvin. And the reasons are twofold. The first one is we need to make sure the system has enough kinetic energy to overcome the barrier. The second is we want to reduce the duration of trajectory. If we run, say, molecular dynamics at 500 Kelvin, maybe the duration will be up to nanosecond. So here we use 2000 Kelvin, and the duration is just 1 picosecond.
Can I continue? So maybe there is another reason we didn't keep it in mind while doing, but in your talk an hour ago, you so intentionally bring system into the top of the barrier, but it is possible if the expected reaction is known. If one can put a guess about a reaction, but if you have like several unknown pathways, then we do not know where to put, and we let the system explore possible pathways, which is quicker to high temperature.
Okay, here is the results from my trajectory. And so here we track the bound distance of different pairs. The blue one corresponding to distance between nitrogen and carbon. So as we can see, as time goes by, this distance between becomes larger. That means breaking is happening. So for example, at Q 150 per second, the nitrogen is far away from the carbon. And the red means distance between bromine and hydrogen. So as we can see, as time goes by, the bromine just approach hydrogen. And at this time, we can see the formation of the hydrogen-bromine bond. And this bond is quite stable. As we can see, at the later stages, we can see the fluctuation of this bond. This is a hydrogen-bromine molecule. And finally, the phenol group just kept on the surface of the silicon. As we can see, this is a green curve.
The temperature, I forgot you mentioned.
2000 Kelvin.
2000, yeah. So could I ask or just make a remark? So you run at very high temperature because then you see all the processes happening. Otherwise, it doesn't. Have you considered doing like parallel tempering, which is a technique where you run at various temperatures from 300 to 2000 and like 5 or whatever temperatures in between, and then you swap the configurations between the different temperatures, and so that means that in the end your low temperature trajectory also has initial stages somewhere that came from high temperature. So then you do a sampling at low temperature where you also arrive at product state kind of configurations, but still measure like at low temperature.
So if you have two trajectories, one high,
You
another
swap.
low, you instantly hit one, and
Yes,
instantly
exactly. You swap the temperature.
freeze another
Yes,
one.
yes, yes, yes. So that is a way to, well, to cross these high barriers. But then, say the sampling you do at the low temperature is so there you really measure what happens at that temperature. So in this way you have like you do effectively a low temperature simulation, and these high barrier processes you also have included in them, those in your sample.
What kind of consequence by this kind of swapping do you expect these two trajectory will converge?
Well, it's like a way to it's like a way to improve, well, also to force to be able to have these reactive processes where you need a very high temperature. Well, to impose them your run, but measure everything at lower temperature.
So after making this procedure, one monitors and reports
Yes.
only the lowest temperature.
Yes. Yes.
It's to some sense it is a way to spawn over broader
Exactly.
distribution
Yes.
of initial configurations.
Yes. So what you do is the high temperature one, which you are running, you're used to explore all kind of very improbable configurations, which are necessary because you break the ones. But in the end, you use these ones to run, to sample, to measure at the ordinary temperature, where maybe everything is happening in reality. It's a trick. Yeah? It's a trick. But,
So what's the name of the trick?
parallel temperature.
Parallel temp.
So you run in parallel
Huh?
at different temperatures.
Interesting. So, I guess based on our molecular dynamics calculations, we found that by using diazonium salt, we can actually cap the silicon surface with phenol groups. And then at this stage, we want to just compare electronic properties of different slabs. This is a bare slab without any ligands. This is a hydrogen pacific slab. This is a phenol pacific slab. So here it's PDOS. So basically, the electronic properties of hydrogen pacivated and phenol pacivated is quite similar. For the bare slab without any passivation, it's a little bit different. So as we can see, this is a potential spectrum. So there is a new feature for the bare slab at this regime. Yes, here is just some physical properties. So this is that's the states for the phenol pacivated silicon slab. This is the potential spectrum. So previously we used high temperature molecular dynamics to capture the chemical reaction. Here we use room temperature molecular dynamics just to provide a basis for our non-adiabatic coupling calculations. So from room temperature molecular dynamics, we can get some interesting formations. So this is an overlap of several trajectories, as we can see. So the vibration is significant for phenol group and also silicon on the top and on the bottom. But the middle one experiences no reaction, no motion, or very slow motion. So yes, the rest of it very interesting. That's it. Oh, okay. Good, thanks. Any more questions? Okay, well, let's thank all speakers of today once again. Meeting is dismissed. If you want to talk to each other informally, feel free, but I think it was enough for today.
Okay, I thought the meeting was going to start at 5 today because of that chemistry meeting.
We started a little earlier,
Okay.
but you didn't miss. We started maybe 20 minutes before 5.
All right.
So you didn't miss anything. There is one thing that we will not cover like right now for everyone, but David and Kevin are running most challenging part of the computational procedure. They're trying to convert MD into non-adiabatic couplings, and this procedure always gives a lot of errors. So first, jobs are waiting in the queue.
Mm-hmm.
So you run and you do not know if you do things correct, and like a week later you found that everything is wrong, and then after job started you analyze output and it may give something you are not expecting. So please contact other group members.
Okay.
So Dr. Han, Aaron, me, Dr. Fatima, if something is not going as you expected, I hope that each of us will be happy to answer and troubleshoot.
All right.
So it is very much needed and expected that in a week from now you will see you have coupling files like coupling 001, coupling 002, and they should be non-empty file. If you look, it should be like text data with matrices. Each coupling file is like matrix 100 by 100.
All right.
So do not hesitate. It's better to give a signal of things going not right earlier than later.
Right.
Okay, then next meeting is in a week from now at 4, and there will be some presentations on converting couplings into graceful tensor.
All right.
So is this your last stop?
No, I'll move on to Vancouver, Canada.
Vancouver.
Yeah, so that's still further
Mhm.
west.